We are going to start this chapter with Fermat's Little Theorem. Don't be scared of the term theorem. This is a little theorem. It's going to be a lot more easier and a lot more fun. We are going to sharpen our skills. I mean, what are all the concepts that we have learned so far? We are going to apply all the concepts that we have learned so far at a high level. You don't have to memorize the Euclidean algorithm or the extended Euclidean algorithm or the safe GCD or extended safe GCD to find the modular inverses and everything. Okay, the thing is that you need to be able to reason conceptually. Right? The conceptual reasoning is necessary to understand the Bitcoin improvement proposals, the cryptography discussed in Bitcoin improvement proposals, or the mailing list, or the papers. Right? There are so many zero knowledge proof innovations is happening in the field of zero knowledge proofs and so on. So, not to digest them, you need to develop the ability to apply this concept at a high level. Right? So, this theorem is going to help us improve that skill. So, this theorem states that for any positive integer of this form, okay, p is a prime, right? So, p is prime. We have a to the power t minus 1 is congruent to 1 mod p. We are only dealing with p which is greater than 2, right? So, imagine p is a very large p. So, in that case, we get a times a to the power p minus 2 is congruent to 1 mod p, which means this particular term a to the power p minus 2 is the inverse to the element a. So rather than going the tedious way that we did extended Euclidean algorithm or the safe GCD to find the multiplicative inverse, we could have simply computed a to the power p minus 2. Even though p could be a very large prime, this exponentiation could be done fairly easily in modern computers. Right? There are efficient algorithms to do that. The efficient algorithm will run with at most big O of log 2 of p. Right? So this is the complexity analysis in data structures algorithm. You can just look it up what this big O notation is. Just Google big O notation. Okay. This is fairly easy to do. But I think the drawback of this algorithm is that this uses multiplication of possibly very large integers. And multiplication of very large integers is not as efficient as the safe GCD algorithm that is implemented in the SCP 256K1. Right? So that's why Fermat's Little Theorem is not used there. Okay. But how do we prove this? Right? We are going to use all the concepts that we have learned to prove this theorem. Since A is of this form and P is a prime, we can confidently say that GCD of A comma P is equal to 1. Because if we consider this set S of all the elements, right, all the multiplicative, we are not including 0 because 0 doesn't have a multiplicative inverse. So we are essentially dealing with this ZP group under multiplication. Okay, so we have this P minus 1. So this is a set. Any number in this set does not divide P, so we can easily conclude that GCD of A comma P is equal to 1. And from this also we can find, using the Bezout coefficient, we can essentially find the inverse of A. That's what we saw in the previous chapters. Let's consider a different set which is called AS. Here what we do is we multiply every single element by A. So 1 times A, 2 times A, 3 times A, so on till P minus 1 times A. Now the question is, does every single element of this set are unique? Okay, that's the question. Okay. If it is unique, then we can do some tricks to get to the proof. So what if they are not unique? What if you can find two elements of this form, x times A is equal to y times A? It's congruent to y times A. Okay, we are dealing with modular arithmetic in P, right? So have to be careful there. And we know that there is an inverse exists for A because GCD of A comma P is 1, right? From this we can conclude that there is a multiplicative inverse for A. Okay. Yeah, because we can apply the extended Euclidean algorithm, right? So we can multiply by the inverses on both sides, and essentially we can cancel out this A, which means x should essentially be equal to y. I mean, if we assume that there are two terms which are not equal, we get to the contradiction that they are in fact equal. So our initial assumption that we can find two terms in the set, right? So in this computation set, intermediate set, that they are equal, we come to the contradiction that the individual part is in fact equal. So we can assume that we can safely conclude that every single element in the set is also unique, and they are exactly the same as the set S. So our conclusion is that the set S is exactly equal to the set A times S. So let me multiply all the numbers here in the set A, the set S. What do I get? So 1 times 2 times 3 till p minus 1. Here we have 1a times 2a times till p minus 1 a. Okay, we are just these are like congruent. This equality holds because we just have proved that both of the set are equal. So if we multiply them, they are in fact equal. The order of the multiplication might differ, but we know that integer multiplication are commutative, meaning if we do 5 times 3, it is essentially equal to 3 times 5, and it works for modular arithmetic also. So that's why the order in which we multiply doesn't matter. The order of multiplication on the left hand side is different from the order of multiplication on the right hand side, but they are still equal because integer multiplication is commutative. Okay, this is nothing but p minus 1 factorial. You can just look up the definition of factorial. It's pretty straightforward. Okay, I'm just a shorthand form for this. And similarly, here also we can take p minus 1 factorial, and I can take a to the power p minus 1 mod p. So p minus 1 factorial is just a shorthand for every single term here, 1 times 2 times 3, and every single of these terms, right? So if I take any x from this, right? If I take any x from this set, the GCD of x comma p is equal to 1. So every single term has a multiplicity inverse. So essentially we can cancel them out, and we have a to the power p minus 1 is in fact congruent to 1 mod p. Just inverted. You can just rewrite these terms. Okay, you can just shuffle the left hand side with the right hand side. It means exactly the same. So from here only we get this idea of generators. If we take the Z5 group under multiplication, so we have these terms 1, 2, 3, and 4. I have discussed this concept in the chapter 1 itself, but let's redo this. Okay, we will soon realize that not all the terms generate the entire set. The best example is 1. Like 1 power anything is just 1, so 1 does not generate the set. But if we do like 2 power 1 is we have 2 power 1, 2 power 2 is 4, 2 power 3 is 8, which is 3, and 3 times 2 is 6, which is 1. 2 in fact generates, and you can verify that 3 also generates. But if you take 4 times 1 is 4, and 4 times 2, like 4 square is 16, which is 1. So 4 does not generate the entire group. Only 2 and 3 are generators. But the idea of Fermat's Little Theorem is, right, it doesn't matter whether the element inside the set, inside the multiplicative group, whether it is a generator or not, we can essentially say any A belongs to ZP under multiplication. A to the power p minus 1 is congruent to 1 mod p. Okay, so this is what we can conclude. Right. That's the end of this video.